Hello, everybody. Welcome back to my channel. And something crazy just happens in AI. And yeah, have you ever tried to use large language models for your work, right? And typically, what you need is a lot of like NVIDIA GPUs, right? Llama CCP, and it's actually kind of expensive to run them, but allow me to show you what happened a few months ago. So someone just managed to outperform large language models by just using a multi-layer perceptron, right? As you can see, it is performing quite similarly to the LLM, and it in fact outperforms in some tasks. And all the tasks here are in chemistry. To you guys who don't know here, we have a clinic toxicity, predicting whether or not a chemical compound is toxic, or whether or not it has to do with HIV and so on. So this is the question, right? Is it possible, right, to distill a large language model instead of distilling it into a smaller language model? How about we just distill it into a multilayer perceptron? It would be so much cheaper. And so that's what this video is going to be about. And the paper is called LLM and GNN are complementary, distilling LLM for multimodal graph learning. And it's done by a group of researchers in Pennsylvania State University. So yeah, let's get back into it. So there's been a lot of work in graph neural networks. If you don't know what graph neural networks is, basically a network that takes graph images and output. And yeah, so there's a lot of stuff about graph neural networks and how can be used for chemistry, especially to predict the chemical properties of molecular structures. But also, like, if you go back in chemistry, there's a lot of different ways to draw molecular structures. And typically, right, there are like a text and image descriptions of these molecules that the graph neural networks cannot use. So what can we do? Well, we can just simply use large language models that can take these images and text and combine it with the graph neural networks, right, in order to produce accurate responses. So what they try to do here is really ambitious, right? They try to fit in the information from the from the ions and combine it into a single multilayer perceptron. And this sort of logic is really cool because if you can distill it into the multilayer perceptron, you essentially don't need a lot of computation power in order to run these kind of predictions. So if we directly stick to this figure right here, right, in figure one, we see their approach overall. So what you basically have, right, for a molecule, you have the smallest text description that represents the molecule, and you have a chemical diagram of the molecule, and also we have the graph topology structure here using an adjacency matrix. And lastly, you have the element information for each node, right, for each atom, right? And what they did next is pretty standard. All they did is to freeze the weights of the LLM, which is what you pretty much do for knowledge distillation. And after that, you have another language model which takes in the output of these frozen LLMs in order to produce a embedding about the molecule, just based on the smells and the picture of the molecule. And then we have the graph neural network that takes in the topology structure, right, to give you a graph embedding. And last but not least, we have the Multilayer Perceptron that takes in the node features and tries to come up with a representation of the molecule, right? So it's only taking in the node features. That's it, not even the bond dimensions, right? And the idea is that you perform distillation by taking these two embeddings, these two representations, and try to get it into this NLP representation. So let's see what I have to say, right? So if we take a look at some parts, some are pretty self-explanatory, but I think, yeah. So if we go here, right? So there's quite a few challenges, right? First of all, the LLMs, right, they struggle with directly predicting the molecular property because they're such general models, but they're not really that great at predicting these chemical properties. And especially when it has to do with classification or regression tasks and analytics. So in order to do that, right, then they have to find a smaller language model that does this kind of classification and regression tasks, if that makes sense. So okay, another one, right? Another problem is that a lot of methods that for graph distillation is only on classification, right? But it is not that common for graph regression, right? Especially in the field of distillation. So okay, what it did, right, is that they used a mapping function that maps the embeddings from the teacher and the students to a latent space where they can do this kind of knowledge distillation process. And I'm pretty sure we'll see a bit more of that in this second. So okay, well, that's not too important. That has been covered, right? So let's go through. Okay, let's start with their approach, right? So as you can see back here, we have an example of the prompt that they use. So first, we provide a general task description of what we want the LM to do. So we are going to assign it to become an expert in chemistry, right? And we also tell it to predict a specific property given the molecule, and we'll be given a small string and the adjacency matrix representing the graph structure of the molecule, right? And not only that, but we also have to tell it what kind of a data set this thing is, right? So in this case, it is about predicting the hydration-free energy of the molecules in water. So and furthermore, we have to tell it to focus on analyzing the properties of the molecule, specifically functional groups, structural characteristics, and so on. And then telling it to make the best prediction of its hydration-free energy. All right. And lastly, we have to inform it about the smells and the molecule diagram, blah, 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 right? So essentially, we are just going to inform the LM about the molecule in sentences, right? So that's that. Now, if we take a look at the notation and the probable definition, right? Let G, graph G be a set of notes, images, note features, right? Smells and molecule diagram, and we will have a data set called DL with its own labels associated with each graph, right? With each molecule in this case, and a LM, right? So we want to learn function that can map between the graph and the label. So that's that. Let's take a look at this. Right, okay. So we have gone through the prompt structure, and obviously we're going to be related to the LM. So that's pretty easy to understand. And now, okay, cool. So yeah. So how do we pre-train the model? How do we even fine tune it? Right? How do we fine tune the entire thing? So okay, as the response from the LM is text-based, right? We have to find a way to make it into an embedding or some type of load vector, right? So obviously we have to find a small language model to become an encoder, so that we put both the smells and the response into this small language model in order to get your needed representations, right? That can be used for your distillation process. So okay, right. So this is basically the equation of that process, essentially, right? And then what we can do next is that we can take this and feed it into a function that gives you a prediction value of that molecule property, right? So the features are pretty So we're okay, right. So in the next, right, you have to pre-train a graph neural network with the graph structure and the node features, right. So it's start this equation here, and then you get this hidden embeds, which you can feed into another transformation function in order to get your GNN prediction output. So as you can already see, right, we have one from the LM and another one from the GNN, and you see how we can combine these two together in the objective loss function. So let's see, okay, now here's the most important part. How do we form knowledge distillation, right, from the LM and the GNN into the NLP? Well, it's actually pretty simple, right. So all you have to do, right, okay, all you have to do is to do something. All you have to do, let me see, is to perform this kind of operation here. So what you need is to get the prediction value from the NLP and from the LM, right? And you try to minimize the discrepancy between their two different prediction values for the same molecule. You also do the same as well for the NLP and the GNN. In such a way, what you're trying to do here is that you're trying to let the NLP tell it to produce an output that kind of matches the LM, but try to match the GNN at the same time. So it's going to be somewhere between most of the time. And it really depends on hyperparameters such as alpha, and beta, right? It depends how you use it, right? With the LM prediction values, if you increase the alpha value to a high value, or the beta value to right? So as we already know, the NLP is nothing more than just taking in the node features and feeding it into a set of linear layers and activation functions in order to get that prediction output, right? So that's pretty self-explanatory, right? So let's see right here. Yeah, you have to combine this as well. So you also have to make sure that the NLP prediction value is closely matched with the ground truth value in this case, right? So the section right here called representation distillation. So okay, right. Okay. Given that LM and GNN are trained independently, their respective representations exist in different feature spaces. So they're trying to align these different representations in the same space by transforming them into a common data space. So what they have to do in addition, right, is to have this U function here, U NLP, U LM, and U GNN in order to get them into the same vector space, essentially. So but I'm not sure whether or not they define this function. Obviously, this is another neural network. In that case, it depends, right? So so it's pretty much the same, essentially, right? So it's pretty much the same. So it is similar for classification and regression. So that's that. And now let's take a look at the experiments. So there are 4 research questions that they're trying to address. So how does their approach perform compared to GNN and the large language models? And do both GNN and the LM contribute to the pretty good final result? And to what extent does the multimodality, right, the text approach help with the LM prediction? And also they want to know whether or not using different LM models would affect the performance of the NLP. Well, which find out right now. Okay, so here's the experimental set, right? So this is pretty much standard, right? So they're going to compare their model with GNN models of different kinds, revolution neural networks, RAP-SAGE, GIN, Lower, and different NLP models, right? And just note here, right, all these models that I mentioned, it is mostly specialized for chemistry tasks. Some like small transformers and these are just for chemistry, right? So if we take a look at the results, you can see that their approach is actually pretty good, right? It is actually the state of the art, right, in terms of these predictions, with some exception, especially for the heavy solubility and predictable fidelity of the molecule. And that's about that. Okay, now let's go through, right? We already saw this figure from the beginning of this video. You can see that by just training the NLP by itself, right, it doesn't really achieve better accuracy in some way, right? Yeah. But if you give it more information, right, from the LMs and the GNN combination, right, it really pushes the NLP prediction accuracy to the max. So that's particularly here. Let's see if we have more examples here. All right. Okay, as for the multimodality, they found out that by combining all the different information features from each modality really helps. So okay, let's say to be more specific, removing multipliers result in significant performance drops due to the lack of already other molecule such as some functional groups. And well, it really okay, I'm gonna say one thing about this statement later on. But let's see. All right, figure 6 illustrates the different performance of different LMs. These are the image language models, image text models. So right, there's figure 6. Figure 6. Okay, figure 6 actually somewhere here. So find it. Figure 6. Okay. Right. As you can see, right, in figure 6, the performance of the framework is kind of impacted, right? But you can see, right, Clock Haiku and Clock Sonnet performs kind of similar, right? Despite their parameter differences. Well, see how their parameters. Clock Sonnet parameters. Right. So Clock Sonnet is let's see, Clock Sonnet and Clock Haiku parameters. Right. So right, it seems like this one is actually called Haiku, just around 20 billion parameters. Clock Sonnet is 70 billion parameters. But you can see definitely the more parameters can better the performance after knowledge distillation is going to be because it's more useful information than some model. But not like it's compact. Especially the parameter increased by like twice. So that's that. GPT-4V parameters. Let's see. So GPT-4V in the dimension here. Is it on 100 base? Yes, it's on 100 base. Okay, I would say GPT-4V might be smarter, perhaps. Does it use anything like that? Okay, right. I don't think that really matters. So in any case, it's quite similar, right? In terms of the BSE task. But as for predicting the blood-brain barrier, right, this GPT-4V is actually better in this case. All right. And now let's take a look at figure 5. Okay, for predicting clinical toxicity of the molecule, if we discard out the diagram, it drops immediately. But if we discard out the structure information, it remains the same. Well, but however, right, for a blood-brain barrier, if you drop any of them, the performance drops as well. That's the same for the ACD. Right. So okay, right. So the main takeaway behind this is that multilayer perceptron can outperform LMs, right? But there might be a word exaggerated here. But I think there has to be more work done, right? Especially to create an alternative, right? An alternative cheaper way to do natural language generation, perhaps using this kind of approach. And also right now is limited to classification and regression tasks. But